Alright, so in this video lesson, I am going to show an additional example to calculate the volume of a solid that's generated by rotating an area around a given axis, but by using the cylindrical shell method. Okay, and so this video lesson, this short video example is highly recommended to be viewed after you have watched my general discussion lecture about the cylindrical shells method. And of course, it should be viewed after you have learned what the fundamental theorem of calculus is. Okay, and so let's get to it. And so here is the wording description of our problem right here. In this problem, we would like to find the volume that's formed by rotating about the y-axis, the region enclosed by the two curves. One of them is x equals 8y, and the other one is y cubed equals x, with y being positive, I mean y greater than or equal to 0. Okay, so let's extract the information here one by one like that. And then in the meanwhile, as we read through the description here, I will swing back and forth between the wording description here and the graph, so that we can see the regions first, and then we're going to imagine how we're going to rotate that region around the y-axis. All right, so the two curves we are given here are x equals 8y and y cubed equals x. So these are just any two curves. These are just any two graphs. And then this is how they are given in the way they are currently expressed. So the curve here is expressed as, one curve is expressed as x equals 8y, and the other one is y cubed equals x. Like that. So let's see what those two curves are. So on my graphing space with decimals right here, then this is the curve for x equals 8y. Like that. Okay, this curve, that's the one. And then this curve is the curve for y cubed equals x. So this next one that just popped out right there. Okay, and so in that way, after seeing the two curves here, then the description of the problem is saying that we want the area that's enclosed. So the area here is the region that's enclosed by those two curves. So where can that enclosed region be in our graph? It has to be this area. Now let me zoom it in a little bit, but it has to be this area here, and there's another area there. So there are actually two areas. It will make no sense to be the area out here or the area out there, neither that one, because these are not area enclosed. It will be infinitely bleeding out, or it will be limitless out there, or boundedless. And so the only enclosed area are these two. So let me now put in the shading right there that describe the areas that we are looking at. So the area we're looking at has two little regions, two little sections here. Okay, and so now I'm gonna put away all of the unnecessary parts here, and I'll only retain the shaded area in our picture. All right, so that's our shaded area. But now, since we're still having two shaded area here, then let's look back at the wording description of the problem one more time. Okay, so the wording of the description says, so we want the area, the region enclosed by the two curves, but on the other hand, we have another requirement here. We want the area that satisfies y being greater than or equal to 0. So that means in the two regions we're looking at here, we're looking at this region here to my right, okay, is the one that satisfies the requirement that all the y values is positive, because it's in the first quadrant. Okay, and so this region here is the region that's going to be rotated around the y-axis according to the description of the problem like that. And so now I'm going to switch over to the 3D view to show the demonstration of the rotation. And so on my 3D view, I'm gonna only show this part of the region where it's above the x-axis, where the value for y is greater than or equal to 0. So there's the region. Now in the 3D view, it's shaded in blue color right here. And so now I'm gonna rotate this region around the y-axis. And once again, the rotation orientation should not matter here. So here's the solid that what it will form after the rotation. Okay, so And let me zoom it out a little bit so that we can see the complete shape of the region like that. All right, and so now that's how it happens when we're rotating that region. And then this is about halfway of the rotation like that. Okay, and so now, and I also put the picture of that of a shell there, because the idea now is that we're gonna use a cylindrical shell method. So this is the picture of one shell, and those shells can happen from, we can have the shells that go all the way from the outer part right here, okay, and to the inner part like that, okay, and we will get more into that. All right, so now I'm going to switch over to my writing board. Okay, and so let's now have an actual hand sketch of the picture like that, so that I can put in more detailed explanation about how we construct the shells and all that. So according to the problem, we want to rotate the region around the y-axis. Okay, so the y-axis is the axis of rotation. And so now in that way, here's the picture again. That and of course, forgive me that I'm not able to make the exact picture as how the computer was given, but it should be good enough for us to see. So here's our curve. This curve here is y cubed equals x. So right now that's currently the way how it's represented as an equation. Y cubed equals x. And then it has an intersection. It has an intersection with the curve. So this other curve here appears to be a straight line over here. And this curve is, x equals 8y. Okay, and then in that, this is the x-axis, this is the y-axis, and the area that we are, the enclosed area is here. That's met all the requirements. Okay, so with that area that now we are rotating around the y-axis, so the rule that we have learned through the general discussion with the cylindrical shell method is that when we're using cylindrical shell method to calculate the volume of the rotated solid, then to calculate the volume of that solid after the rotation, then the stripe that we're using here has to be parallel. So rotation axis is the y-axis here in this case, in our case. And so we must use a stripe that is parallel, okay? And that's how you saw in the picture, the animation picture earlier. So the stripe has to be parallel. And then now once rotated, put that in your imagination that once rotated, we are going to create for ourselves a shell, like a drum shell. Okay, and that's why, formally speaking, it's a cylindrical shell like that. So that shell now has any of the shell here. So we can place a shell out here, and we have a lot of shell going from the inside out. And again, just like how I explained in the general discussion lecture, then inside means if the shell or if the stripe is, whichever the stripes are closer to the rotation axis, that's the inside, and then outside means we're going further away from the rotation axis. And so our rotation axis is here, okay? And so now, this is the shell height, okay? This is the height of the shell, and each shell here has a thickness. And so in the way how we place the shell right here, this is the thickness. All right, and then each shell has a thickness, and each shell has a radius. Okay, that comes out. So basically, the radius here, in the way how I'm drawing the picture, the radius simply just the space, the horizontal, the distance between the rotation axis to the stripe where we place that. Again, it's the distance from the stripe to the rotation axis. Okay, that's how we put that's how we call it. It's the radius. Okay, so this right here in my notation is the radius of the circular cylinder. All right. So now the constant reminder right here, I mean that's fundamental that I was introducing. So the way to calculate any vertical cylindrical shell, or just any shell, this is height with radius, okay, then with thickness, with a little thickness here, okay. Then with any shell like that, and we're going to multiply. So we're going to go 2 pi times the radius. That's the circumference of this base circle on top and bottom. And then that circumference there I am going to multiply with the height. And that height there is multiplying the circumference with the height. That gives me the area of the lateral area. That's a precise term for that. The area that's wrapped around, being rolled around. And then we're going to multiply that with the thickness. Okay, multiplying that with the thickness. And so now that will give us the volume for one thin shell, the volume of one thin shell, just like how I demonstrated in the general discussion lecture, that I used that illustration that I wrapped around, I rolled around a piece of paper from a flat rectangular piece of paper, but we wrapped around into a cylinder. So the thickness here equivalent to the thickness of the unwrapped, the unrolled piece of paper like that. So that's the thickness. And now we're going to be, so this is volume of one thin shell, but we're going to be accumulating all of those the volume, shell volumes from the inside out. Okay, so basically this is start to end. We always start from the inside out. So inside means we start from those shells that's closest to the axis of rotation, and we keep integrating, we keep accumulating further out and further out. Okay, those are shell volumes. All right, so that's the fundamental that I want anyone learning about the shell methods, the shells method with me to keep. Okay, because eventually you're going to be exposed to too many formulas. So I don't want my students to memorize formula. That's not healthy for your learning. So now in that way, now I'm going to put away this picture. So now back to the general discussion lecture. Then I said that it's me that I always, I personally work better when I start out with finding the thickness. So thickness is the first thing I'm finding here in these picture problem. So step one right here, thickness is easiest to identify. So thickness here is just simply how thick the stripe that we place. And keep in mind again, the fundamental, the key idea here is that the key characteristic here is that we place the stripe to be parallel with the rotation axis. So in that way, parallel with the rotation axis means the stripe has to be perpendicular with this x-axis here in our problem in particular. So thickness has to be consequently dx. It's a change in x value, and then when it gets infinitesimally small, when that change in x gets infinitesimally small, then it becomes the differential dx. Okay, so now I already have a revised, so now I can go ahead and revise my integral. Circumference, multiply with height, okay, for whatever that is, and multiply with thickness, dx. All right, and then from the inside out. And so now getting the thickness nailed down as a d expression gives us an advantage of that indicates for us what to expect in these expressions. So now I know for sure that in the next step, finding radius or finding height, that's pretty much our own order. You can find height before finding radius, or you can find radius before finding height. That's pretty much your choice. But both of these are all both of these must be expressed in terms of x. That's the idea here, because the d expression here is indicating it for us. All right, and so I might violate my own order in the general lecture a little bit, but like I said, finding radius or finding height is pretty much at this point, whoever before the other one, that doesn't matter. So how about radius here? The radius from wherever I pick my stripe, that's just simply the x distance from the rotation axis. The rotation axis we have for ourselves here is on the y-axis. So any stripe that we put here is basically just an x distance. So here we add a distance, we add a value x, okay? And so now that means radius, okay? And at this point right here, we have quite some massive amount. I have to erase some extra note right here. So at any x right here, that's going to be the radius for us, okay? And so radius is going to be x. All right, and so now in that way I'm going to again come to a further revised version. Circumference now, 2 pi r, 2 pi times x. That's my circumference expression for the base circle of that shell right here. All right, so now let's just figure out the height right here, the height. So now you can see in this picture, the height is just simply the length of that stripe. I put it here vertically standing up from the x-axis. Standing up from the x-axis because the stripe here is parallel with the y-axis. But now if we observe closely, if we observing that a little more closely, I place a stripe here, I can place another stripe there, okay, or I can place another stripe here. Any of my stripe, the length on any of my stripe here is being restricted between, is basically the difference between the lower curve and the upper curve. That's just the way how it happens in this problem. And that's what makes this additional example different from those I offer in the general discussion lecture. Okay, but basically there will be a way to find the height, but here a little bit different from the general discussion lecture, that here any of our stripe has height being the difference between the upper curve and the lower curve. Upper curve and lower curve. Okay, and then so in that way, kind of put that I'm going to put that into our plan right here. So I'm going to work it on a separate space right now for now. All right. So the height here, basically what we see here, what we need here is upper curve, okay, minus lower curve. All right, that's the plan right there, because that's right from the picture. So we have to see the picture of these problems. And so upper curve minus lower curve. And then furthermore, we already had an indication for us that the integral here eventually will be in terms of x. And so now it is our responsibility to ensure, that upper curve is, well, I'm going to make an open parentheses here, in terms of x, okay, in terms of x. And the same with us, in terms of x. We need to make sure both of our curves here, the upper curves and the lower curves, are in terms of x. Do we have that yet? Okay. The upper curve as labeled here, is y cubed equals x. X equals y cubed. It's not quite in terms of x yet. Okay, so now we can do a little bit of algebra, and the same with the bottom curve here. The bottom curve is written as x equals 8y. So none of the curves given for us here are currently represented as functions in terms of x yet. So we have to algebraically, so some problem we have to, like this problem here, but maybe some other problems we don't have to. It all depends on how our given curves are given in the beginning point. Yeah. Okay, but here we have our curves in the beginning, our two curves are not initially written in terms of x. Okay, so now I'm going to have to turn that into functions in terms of x. Okay, so now what I see here, upper curve is y cubed equals x. So to re-express this curve in terms of x, I'm just simply taking cube root on both sides. Taking cube root on both sides, we don't have to do the plus and minus thing algebraically. So that means y equals cube root of x. That's one curve for us. Okay, and then similarly, the lower curve. So this is the upper curve. Okay, and for the lower one, we have started out being x equals 8y, but that means y equals 1/8 x. So now we have re-expressed the exact same curve but in terms of x as a function of x. All right, and so now in that way, the upper curve minus lower curve, and now both curves are successfully written in terms of x. So that means the height here has to equal, in that general plan right here, then we're looking at cube root of x minus 1/8 x right here. This is a formula to determine the height of our stripe at any x instance, at any x value on the x-axis. Okay, and so now in that way I'm going to come back to my board because everything there was just a scratch work. So now the height, right, of the shell. Now we're looking at cube root of x minus 1/8 x. Okay, cube root of x minus 1/8 x. And now we have a formula. That represents the height of our shell at any x value. See, we place it here, or we place it there at any x right there, at any x. That height right here is simply just the difference between upper curve and lower curve. And now I can fill this expression in that empty parentheses right here. So now I can revise my current integral as cube root of x minus 1/8 x in parentheses. And now that completes our, almost complete our integral. Okay, so let's now find out where's the start and where the end of our accumulation work. All right, so just like the way how we're looking straight right there at the picture, the first stripe, the starting stripe has to be where it's closest, wherever it's closest, wherever in the region that's closest to the rotation axis. And when we're moving from the inside, we're accumulating from the inside out. So in that way, it looks like, and we can spend some time solving it. Okay, and so now I'm gonna once again swing over to the other board for a little bit of scratch work right there. But how I see it, now upper curve is here, lower curve is there. We just need to find out which x values making the two curves here cross. So algebraically, I can set both sides equal. Set the two curves equal to each other, because this is how I want to find the x values where the two graphs here crossing each other, where the two graphs here are crossing each other. Okay, so cube root of x equals the x, and so that means I can multiply the 8 to the left hand side. 8 cube root of x looks a little bit too much like an 83. So 8 times cube root of x equals x. But now to get rid of the cubic right there, then the cubic root right there, then we're gonna raise both sides to the third power. So now I'm looking at 8 cubed times x, okay, equals x cubed. All right. And really, we can write that 8 cubed here as 512x equals x cubed. And so now we can solve this equation here by subtracting that x term to the other side. So I'm looking at x cubed minus 512x to equal 0. And we can factor out the x here. Okay, and then we have x squared minus 512 equal 0. Okay, and so that means I'm having one solution here is x equals 0 for that factor. And then this factor, this x squared minus 12, minus 512 right here, I can have x equals plus and minus square root of 512. But but the plus and minus square root of 512. Now, technically, we had two solutions, but our graph here stays on the positive x-axis. That means we're only going to choose the positive square root. Okay, so now I'm going to ignore. So I had to write it down in both ways, in both signs here. I had to write down two solutions, but now for our application here, we are going to ignore the negative 1. We don't need the negative 1 because remember I showed the graph, our enclosed region is only on the positive x-axis. So that means the two places, the two x values where the two graphs crossing each other, there are x equals 0 and positive square root of 512. Okay, and so now this is, and x equals 0 is closer, according to the way how the picture looks, x equal to 0 is closer, or indeed is right at the rotation axis. So this must be, this x value right here must be square root of 512 like that. Okay, and my picture might be a little too squeezy like that, but now I can complete my integral setup from the inside out. I'm accumulating my shell volumes from 0 to positive square root of 512 like that. That's how we're doing it. And so at this point, the integral setup is complete. The volume to calculate, the volume can be calculated. The volume of this rotated this solid that's generated by rotating the region can be calculated by this completed integral using the shell method. Okay, and so now at this point, I am going to erase this sketch of the work, and then I'm going to use this space right here to get the integral here evaluated. Okay, so now I'm going to evaluate that integral. So in the next step, I can see that I can go ahead and, now the 2 pi is a constant coefficient. So I can pull it out front, okay, and then the integral becomes accumulation from 0 to square root of 512, and then I have, and I can, at the same time, I can multiply the x with each term here, and so now it's going to be x cube root of x minus 1/8 x squared with a dx. And keep in mind, this x times the cube root of x, allow me to make a little note right here. This is really the same as, this is x to the power 1, but this is x to the power 1/3. So 1 plus 1/3 is a 4/3. So altogether, this term here is an x to the 4/3 power. So make a note of that for me. Okay, so now, according to the fundamental theorem of calculus, we are going to need to find the antiderivative of this function. But they're all quite simple power rule functions. And so antiderivative says, so it's 2 pi. Okay, the first term gives me, and so x to the 4/3, so seeing x times cube root of x as x to the 4/3. So taking that antiderivative, it gives me x to the 7/3. But I need to multiply with the coefficient 1 over 7/3, which is a 3/7. Okay, so 3/7 times x to the 7/3. And then I'm going to subtract 1 over 24 x cubed. And then we want to evaluate this from 0 to square root of 512. Okay, so that's what we will be doing right here. Okay, so the advantage of having a 0 in the low end right here is that once we substituted that in here, it's all going to be a 0 out. So mostly with this problem, we're just going to worry about substituting square root of 512 into the expression of x here. Okay, and so now that will give me, so I'm looking at 2 pi, okay, as an actual calculation, times 3/7 times square root of 512, but raising that to the 7/3 power. Okay, and then I'm subtracting 1 over 24 times square root of 512 to the 3rd power. Okay, and then it's subtracting completely a 0 out due to substituting that 0 into each term here. Okay, and so we're very close to being done with the problem. So allow me to quickly step over to my computer station right here and grab an answer, and then I should be back with that final answer right there. All right, so for the final answer, it is going to be more complicated to write with the exact expression. So in this time here, I'm a person who's more who's most of the time favor writing answers in exact expression. But in this case right here, it's simpler to write the final answer in decimal. So my calculation shows altogether. So the final calculation altogether shows 866.5737. All right, and 4 decimal, 3 decimal, how far we round? That's up to, you know, that's up to we watching for the requirements in each of the problems that we're doing. Okay, but this is the volume. Okay, this is the volume of our solids here that's generated by rotating this enclosed region around the y-axis right there. Okay, so this problem here has a specialty in a sense that it introduced the situation where it was not introduced in the general discussion lecture. So here the height or the length of the stripe is being restricted between some two curves. So we just simply take the difference of the two curves right here. And so depending on the way how we place the stripe, right in this picture, it's a vertical standing stripe. So the height there has to be the difference between upper curve and lower curve. Okay, and then in some case, if you have, it was not in this problem, but in some other case, if we had to do a problem where, okay, so in some other case, if we have to do a problem where our stripe between the two curves, but our stripe must be placed, if the problem is asking us to do as a shell method, and the stripe we're placing is parallel with the x-axis, then in that case, we're looking at the right curve minus the left curve right here. That determines the length, okay? The length of the stripe right here, that's just going to be the right curve, okay, minus the left curve right there. That's how it happens. Okay, and then of course when our stripes are being parallel with the x-axis, then each of the curve here has to be expressed as a function of y. Okay, so we need to express this as a function, some function of y, and then this other curve here as a function of y, h of y here, if we are rotating around the x-axis. Okay, and so that's the specialty about this problem that I would like to point out right here, where we determine the length of the stripe here as the difference between the two curves. Okay,